Okay. Hey everyone. My name is Christian. I'm one of the CS3230 TAs this semester. And this slide will be dedicated to revise a little bit on the math prerequisites. Okay, so my contact details are here. Should you find any mistakes or not clear, you can contact me with this via this email. So let's start with a little bit of motivation. So in CS3230, we'll need to do quite a bit of proving. So you should try to refresh your discrete mathematics, your CS2231S or equivalent when necessary. So I understand I was a student myself. I forgot my part of my CS1231 at that point of time. And I know maybe some of you are just taking this module after many semesters of not doing mathematics. So yeah, I hope this slide gets you up to speed on some of the math that you might be assumed to know. So again, this is not exhaustive though. I'll just give a quick survey of several concepts, which I think are important that you kind of know, but we just might implicitly assume that you already know, based on my personal experience, of course. So different CS3230 have different things that they require. Okay, so this is the table of contents. Roughly speaking, I'll be talking about maths, some maths, some proofs, techniques, combinatorics, and graph entries. And really, these are just, I think, just basic tools. So like graph entries, I won't be talking about algorithms in details. I will just be talking about a bit of graph properties and tell you which algorithm you should kind of know already. Okay, so let's begin. So yeah, we start with doing a little quick math. And so we'll talk a little bit about sum of arithmetic progression. And this is a very common sum, like summing from 1 all the way to n. So there's a more generalized version, but I will show you how to kind of like derive the sum of AP. And how you can derive it is first by commutativity of the plus. We try to rewrite the sum from back to front, like n minus 1, back down to 2 and down to 1. Okay, then afterwards, we have these two sums over here, and we add everything together, like vertically down. Like you see 1 plus n, 2 plus n minus 1. So these all happen to result in n plus 1. Okay, and remember, like we are adding two sums. So the left-hand side, there's twice of the left-hand side. Okay, and we started off with n terms. There are n terms here. So here, there are also n terms. Okay, and so this results in n times n plus 1 because there's like n times of these n plus 1. And then don't forget to divide by 2. Like from the left hand side, there's 2 over here. So bring it down, dividing both sides by 2, and we get this n times n plus 1 divided by 2 for the sum of AP starting from 1 all the way to n. Okay, the difference is 1. Yep. All right. So going up, this is a sum of geometric progression. So when every term you multiply by a common ratio, a plus a times r plus ar squared. So something like 1 plus 2 plus 4 plus 8 plus 16 and so on. Okay, take note over here for I did the index a bit differently. I started from 0 and here ends in n minus 1. But there are still n terms over here. Okay, so how we can show this is how we can simplify this is we multiply the whole thing by r. Okay, so a becomes ar, and I shifted it here so that it can be aligned with like the original one. So you have something like this. I'll shift everything by 1 position, but this is ar because we have multiplied everything by r. And then what happens next is we try to do cancellations. We subtract the top by the bottom. And we do cancel all these terms in the middle. And we are left with a minus ar power n. And of course, here there's like a 1 minus r. Okay, 1 minus r. And then what we do is we divide both sides by 1 minus r. So yeah, a minus ar power n divided by 1 minus r. And I'll factorize this over here to make it simpler. Pull out the a, becomes a times 1 minus r power n divided 1 minus r. Okay, so this is the simplified form of sum of GP. So here's a little bit more on it. We can actually factor the -1 out from both the numerator and the denominator. Okay, then you can kind of like flip the order inside the parentheses. It becomes a times r power n minus 1 divided r minus 1. I personally use this more often. because I deal with common ratio of like 2, for example. With 2, then the r becomes like 2 minus 1, but these two are equal. So do keep this in mind, and depending on whether you are, depending on your choice of r, it might make the denominator nicer, okay? So here's a little bit of special case. When the common ratio is less than 1, okay, and I should really put like 0 more than 0 or so, I think, then what happens is that as n goes to infinity, r power n goes to 0. Okay, and this is because as r power n, as n goes to infinity, r power n really goes to 0. Like half, you divide by 2, become quarter, divide by 2, become 1/8. It just gets smaller and smaller and smaller and becoming 0. Okay, so here I have a little bit of inequality. So in this module, do be comfortable with inequalities. What happens here is I take the original terms, take the original things, and then let's say I add more terms. So the upper bound is no longer n minus 1, it's now infinity. The intuition here is like I'm really adding more things into this sum. So it has to be the case that the right-hand side is larger than the left-hand side. Okay, and this by this limit over here, you take this formula, substitute r power n with 0, and you get something like a times 1 minus 0 divided by 1 minus r. And this really simplifies to a divided by 1 minus r. So you can kind of say that this sum over here, if the common ratio is less than 1, like something like a half, then you end up simplifying into this, where this is the upper bound. So it's upper bounded by a constant. Okay, I hope that wasn't too confusing. Yeah, and this is the graphical intuition. So meaning to say that this sum over here is bounded by some constant. At this point, I think I might make a mention that even though I have started with I equals 0 and there are n minus 1, and the formula here, there's an n appearing. So take note, this n over here refers to the number of terms in the sum. Okay? Yeah, keep that in mind. So I've provided a little exercise to apply what you have. I won't go through it here. You can discuss this with your friends or talk to me if you're confused about what I'm asking. Okay, so let's begin with logarithm next. So logarithm, I think you might have seen logarithm a few times in computer science. It's quite common to divide by 2 and log appearing somewhere. So logarithm is the inverse function to exponentiation. So when you want to ask things like 2 power x equals 16, what's x? We can get that by computing the logarithm. Okay, and the logarithm graph looks something like this. So comparing with y equals x against y equals to log base 2 of x, you have this graph over here. And recall that logarithm graph grows very slowly. So I've expanded it out a little bit up to x equals to 800. It just barely increased, it just grows very, very slowly compared to like something linear. So logarithm graphs are good. If something is runtime of logarithm, then that's favorable, definitely favorable compared to something that runs in linear time. Okay, so these are some rules that I hope you already know. But if you forget, then that's fine also. At least you get to revise it now. For example, log base a of, we multiply the inside, we can kind of like separate it with a plus here. Log base a of x plus log base of a of y. Similarly for divide. Okay, here's another one. Let's say the inside, the thing that you are taking logs of has a power, x power n. What you can do is just kind of like bring this power down, like over here. Okay, so there's this image that's been circulating recently, like the end of last month. Yeah, and I think this kind of like gives the similar picture here, right? Next up, some simple things is if you take log base a of 1, that's 0, and that's really because a power 0 is equals to 1. Okay, and similarly here, log base a of a equals to 1. Here's something that's slightly trickier. I didn't really know this prior to university. I don't know if that was like me not studying hard enough or anything, but anyway, I just found this out during my undergrad studies in university. So a power log base a of n is actually equals to n. And the intuition here is because like logarithms and exponentials are kind of like inverses, the inverse of each other. So you apply one first and then apply the other, it kind of like cancels off. Okay. So yep, this is exactly what I described. And this is the kind of like the other way around, right? So I started off with the exponential first, the exponential function. And then I take logarithms of it. After I exponentiate, then I take the logarithms, then I cancel it off, becomes n. So it's kind of like the other way around here. These two are the other way around. Here's also another one that's interesting, I think. So you have a power log of base b of c. You can kind of like flip this c and flip this a over here. Okay, I thought that was really interesting. I didn't really expect this at first. So you kind of can flip them. And so if you're not convinced, try proving it. You have the insufficient knowledge to wait, at least based on the rules that I explained earlier. So you have enough knowledge. And because of that, try to prove it. Pause this video, try to prove it. I'll go through it in a bit. Okay, so I'll give you like 1, 2, 3. Okay, I'll now start working on this. I'll first start by equating x equals to a log base b, a power log base b of c. Okay, so I started this off, x equals to a log base b of c. And then I take logarithms of both sides, log base b of both sides. Okay, nothing impressive here. Then I use this rule over here, the one that brings the power down. So this log base b of c, I bring it down, it becomes log base b of c times this log base b of a. Then I do this time, instead of after bringing this one down, I bring the other one up. Okay, so I bring the log base b of a up to the power over here using the same rule, using the exact same rule. And then we just compare the insides. We see that now x is equals to c power log base b of a, and hey, they're the same thing. X equals to x, and well, yeah, this is the same thing. Okay, so I hope you're slightly more convinced now that they're the same. And I think this is quite useful when you can't really, like you have something to the power of log. Then try flipping it around. Maybe it will simplify some things. Okay. So here's another one, change of base. So let's say I start off with log base b of a, and I want to change it to base d, right? Some other base. Maybe I don't like the number b. I don't like the number 2, right? Then maybe I'll change it to log base pi or something. Itchy hands. So you can just do this, like bring the a up, log base of whatever you want, times of that a in the numerator and this in the denominator. Okay, so with that, I've given a summary over here. Do have a quick look. And before I wrap up the part of logarithms, I want to talk a little bit about log of n factorial is O of n log n. Okay, so I'll just assume that you know big O notation somewhat. I should, at this point, I think you have seen enough undergrad classes to know at least of big O. Maybe the formal definitions, you might have slipped your mind a little bit, but that's okay. Just get the intuition. It's an upper bound, right? So we started off with the log of n factorial. And then what I do first is I expand the factorial, log of n times n minus 1 all the way to 1. Okay. What I do next is I use the rule that this times inside, I bring it out, becomes a plus. Okay, so this repeated application of log of AB equals to log A plus log B. I hope this is clear so far. Then this part, I suspect some of you may be confused by this part. Here I'm taking an upper bound. So again, this is the part where I say try to be comfortable with inequalities. It can simplify some of the things you're working with. So here I'm just saying that log of n is greater than log of n minus 1. And log of n is also greater than log of 2. Log of n is also greater than log of 1. Okay, and so I use this property and I just give an upper bound. Okay, make it easier. And the reason for this is really because the log function is technically the term is monotonically increasing. It's a monotonically increasing function. So we have this property where I have log n is greater than all of like log 1 all the way to n minus 1. Okay, so next, we just recall that we have n terms over here. So log n plus log n, there are n such terms. And because of that, and the reason is really because we start off with n factorials expanding to n terms, right? We didn't drop any terms here. There are still n terms. So we can just do, this is like repeated sums, it's just multiplication. So it's upper bounded by n log n. So here we've shown that log of n factorial is upper bounded by n log n, meaning it's basically O of n log n. Okay, I hope this is clear. You might see this a few times. I believe even in your first lecture notes, there are some mention of log of n factorial. Right, so here's a little exercise on logarithm. So you know rules of logarithm already. Try to simplify this. It looks scary, but if you try to work it out, you'll see some pretty nice things, I believe. Then I'll ask you to prove the lower bound. So it happens that log of n factorial is also big of omega of n log n. So it's actually combining these two facts that actually theta n log n. But try to show this just try to show this. Okay. Next up, I'll talk a little bit about binary to decimals. And really, I'm talking about this because I feel that based on my experience, it seems that a lot of things just assume you know how to convert from decimal to binary or like the bit representation. We are computer scientists, okay? Things are represented with zeros and ones in the low level, right? So sometimes when we describe algorithms, we also analyze in terms of its bits, okay? So it's important that you are comfortable, at least know some of the things about bits. So let's say if you have n bits, right? And binary, n bits, you can represent integers in decimals from the range of 0 all the way to 2 power n minus 1. So what I mean here, let's say with 4 bits, you can represent all the way from 0 all the way to 15, which is basically 2 power 4 minus 1. Okay, so I hope this is okay so far. Next up is the other way around. What if I started off with an integer and I want to represent it in binary? How many bits do I need? And it turns out that it takes a floor of log base 2x plus 1. And so here's a table. You can pause the video to stare at the table and try to convince yourself that it's really the case. So what's important to note is, okay, this looks scary, like there's a floor of log and then plus 1. You might be worried off by 1, but hey, we are computer scientists. We make off by 1s like often, although the goal is not to make off by 1s. But fortunately for us, big O lets us be a little bit imprecise, a bit of leeway. We can just say that it takes O of log of x bits to represent, okay? But of course, do know like what the precise number is so that in case you need to be precise, you are ready, right? So yeah, I will leave it to you to look at this table and just convince yourself that this is the case. Try with some examples. Next up, I'll talk a bit about matrix. And personally, although matrix, I don't quite see it too often, but I've seen algorithms involving matrices as well, like some nice algorithms involving matrices. So yeah, I'll just revise this here in case you do need it in the module. And I believe some other modules also need. In the past, I used to take like machine learning and computer vision, which sees a lot of matrices. So it's revision as well if you're taking such modules. So let A be matrix of size Mn, then Aij represent the matrix along ith row and jth column. And here I'll just use one indexing. I know we are computer scientists, usually we start from 0, but here I think I just want to show if I have a size of 3 by 4, matrix is size 3 by 4, then really these are the index, okay? So I have a matrix here, 3 by 4 matrix, and the 2, so along the second row, down the third column, using one indexing, that's the 2, 3, and 3. The matrix value is 18, okay? With that, let's talk a little bit about the matrix transpose. And you can think of it as like drawing a diagonal across from the upper left corner down to the bottom right corner and try to flip it across that diagonal, okay? So it gets a bit confusing in case like you are you don't have a square matrix, you have something that's rectangular, but I like to think of it this way. So this is the formal definition. The ij entry of the B is the ji entry of A. But I like to think of it this way. So I take the first row and then it becomes the first column. I take the second row, then it becomes the second column. I take the third row and then it becomes the third column in the transpose, of course. Okay, so I hope this is clear. Next up, I'll talk a little bit about special matrices because who knows, maybe you'll face them a little bit. You might need to argue some things based on their properties. So of course, we have the identity matrix, which is just ones along the diagonal. We also have diagonal matrices, which are like, it has values only in the diagonal. Everything else is 0. But the values in the diagonal, well, it can be anything. It can be not just 1. It can be 3, 2, 3, 0, like here. Okay, then symmetric matrix is the case with, if you have a square matrix, then if you kind of like do a transpose, the formal definition of symmetric matrix is really A equals to the A transpose. So you can see that this 2 over here is symmetric along the diagonal. Okay, like 2 equals to 2 here, 3 equals to 3, 3 equals 3 here, 4 equals 4, and so on. Okay, then these are some other matrices. We have what we call the upper triangular matrix, and we have what we call the lower triangular matrix, where the upper triangular are all filled and the respectively lower triangular are all filled. Everything else is 0. Collectively, we usually call this as the triangular, just the triangular matrix. So it can refer to either one. Okay, I see this less often, but I guess it's good to know this as well. Next, let's talk a bit about the matrix multiplication. I think some people might not exactly remember how to do matrix multiplication, and so let's revise that. Let's say I have a matrix of size m by n, and then another matrix B of size n by p. If you try to multiply them together, you can produce a matrix C with size m by p. So take note, it takes the columns of A, number of columns of A has to be equal to the number of rows of B. So, sorry, so let me repeat. So you see here, the columns is n, number of columns of A is n, the number of columns of rows of B, number of rows of B is n. They have to be equal, they have to match before they can multiply. And the resulting matrix is size, number of rows in the new matrix is the number of rows in the old matrix A, and the number of columns in matrix C is equals to the number of columns in matrix B. Okay, and yeah, so generally matrix multiplication is not commutative. I didn't put it in the slides here, so meaning A times B is not necessarily B times A. Okay, so this is the mathematical formula to compute the entry, the Cij entry, and yeah, in case this is confusing to you, let me give a graphical representation, like a diagram with diagrams. So I have this 3 by 4 matrix here times 4 by 2. First, just check, do the dimensions match? I have 4 here, I have 4 here, great. Number of columns equals to the number of rows here. And so the resulting matrix is a 3 by 2 matrix. Okay, and how you can compute this is you just take the row of the first matrix and the column of the second matrix, and then do a like pairwise multiplication. So 0 times 0 plus 23 times 2 plus 4 times 3 plus 7 times 4. And hopefully I used my calculator correctly and computed that it's 86. Okay, and you can repeat this until all the cells are filled. So move the columns accordingly, then move down the rows, and so on until everything is filled. Okay, so there's matrix multiplication. And so here's the exercise for matrices. For you to kind of like understand matrix multiplication better, let's try to analyze. Let's say somebody implemented matrix multiplication. And here I'm talking about the matrix multiplication using this formula. Okay, so in this module, I think you'll be talking about more advanced techniques to do matrix multiplication via divide and conquer, for example. That runs slightly faster than the naive way. But let's focus on the naive matrix multiplication that I just described. Try to analyze the time complexity. Let's say you started off with a square matrix of size n. And then a little bit of extension. What if they are not square? Like just now, as I mentioned, A is size m times n, and B is size of n by p. What's the time complexity? Okay, great. So this is matrix. And yeah, next up, we'll be talking about proofs. I hope you're following me so far. Let me grab a quick drink before I go on. I could pause the video, but drinking is pretty fast. Give you a bit of mental break as well. Okay, let's go on. Proofs. As I mentioned earlier, we'll be talking about three types of proof: contradiction, induction, as well as a strong induction variant. Okay, proof by contradiction is, I think, like one of the really nice ways of proving things. First, we assume that what we want to prove is not true. Okay, then by assuming this, you try to go with deduce some consequences. What are the consequences of assuming that this is not true? Then show that the consequences is actually not possible. It's impossible, either by, say, we contradict what we assume. So maybe we say that maybe x is even. Then suddenly along the lines, we conclude things, and suddenly our conclusion leads us to x is odd. Okay, that's contradictory. Or maybe some other fact we already know to be contradicting some other facts we already know to be true. Like maybe by assuming this, suddenly you deduce that 1 is equals to 0. Okay, something like that. Or maybe both, right? So when such a contradiction happens, the only thing, because we did every steps logically correct, the only thing that must have been wrong was our assumption. The first step over here, the assumption must have been incorrect. So by assuming that it's not true, and we relate to a contradiction, what we started off with must have been wrong. We shouldn't have gone to assume that. Okay, then because of the contradiction, we conclude that what we want to prove is true. Okay, I hope that wasn't confusing, but let's go through an example after this. So yeah, this meme is a summary of the contradiction, I believe. So you assume, well, yeah, but actually, no. Okay, so this is an example, a simple example at that. So I tried finding more examples, but more advanced examples require like more domain knowledge or like some nice number theory to go. But I think this is a pretty simple example. So, well, if p squared is even, then p is even. Let's say we assume, p is actually odd. This p is actually odd, right? So I should highlight this p is even as well, like yellow. I want to assume that it's actually odd. I didn't lead myself to an even number. And just recall a bit of number theory. It means it can be expressed in the form of 2n plus 1, where n is an integer. Okay, then what we know currently is two things. Okay, like what we know of the entire situation, our domain knowledge, right, is p squared is even. This is what we started off with. And then by our assumption, we know that p is odd. Okay, this is our assumption. Then what we do, let's do a little bit of math, expand p squared. What happens if I have p squared is even? P squared, using the fact that p is odd, okay, it can be expressed in this form, 2n plus 1. Let's expand it, becomes 4n squared plus 4n plus 1, okay? But this p squared, using the fact that p is odd, is actually, can be rewritten as this form over here, 2 times 2n squared plus 2n plus 1, which is really like 2k plus 1, really, because this is, well, the technical term is closed under multiplication and addition. Integers are closed under multiplication and addition, but don't need to know that, I think. So because this can be rewritten in this form of 2k plus 1, p squared is actually odd. It's actually an odd number. But this contradicts the fact that we started off with p squared being even. Okay, p squared being even. So there's a contradiction here. And what went wrong is actually our assumption that p is odd. Therefore, it must be the case that p is even. Okay, so I hope that's clear so far. This is a really rudimentary example. If you want a more advanced example, I think the classic example is proving that square root of 2 is irrational. I can look it up. So let's now talk about proof by induction, okay? And I use induction a lot in proving things, because a lot of, especially things that are like have recursive structure, okay? Then usually induction just holds. So it's usually useful also for proving truth of statement. Let's say I have a statement Pn here. show that it's true for all positive integers n. And the idea is, usually for induction, we want to show the base case. Show that the base case is true by checking either n equals 0 or n equals to 1. And then the inductive step is this step where you assume at some step before you, it's already true. Assume that p of x is true, px is true. Then using this p of x, px, you show that the next step, px plus 1 is true. So people have different analogies. It's like some people mention that it's like toppling dominoes, like pushing dominoes down and it topples all the way down. Some people also say maybe like climbing stairs. If I can climb to the x steps, can you climb to the x plus 1 step? So whichever analogy works for you. Okay, so usually base case is very simple. The interesting part is doing the induction step. So it's can be pretty scary, like this hamster over here being scared. All right, so let's go through an example. And so this example, I really chose something that I believe is slightly non-trivial to really show you like the power of induction. Let's define this. A space is L tileable if we can place multiple non-overlapping copies of an L-shaped tile. So this is the L-shaped tile over here. You can flip it, you can rotate it, whatever you want to cover the entire space. Okay. Oops, I accidentally colored it. But yeah, so go look at this example. These two are L tileable and convince yourself why they are. Okay, so give you like 3 seconds or pause this video. And yeah, so it's L tileable because, well, you can place the tiles in this manner. So I color coded it, but I also gave letters to it in case like the colors isn't exactly clear to you. Okay, 0, yeah. So these are the L tiles you can use. So these two spaces are L tileable. Now here's the question, right? Let's say I have this 2 power n by 2 power n space, but then I remove the bottom right corner. Okay, then I claim that this is actually an L tileable space for any, oops, I made a typo here, sorry, for all positive integers n, right? So n is all positive integers. So I made a typo here, apologies. So yeah, so here's the statement. Let pk be the statement, the 2 power k by 2 power k space with the bottom 1 by 1 corner removed. Let's say it's tileable. That's our statement, right? The base case, start with the base case, is very simple. We start out with k equals to 1, then 2 power n equals to 1 here, 2, right? Then this is simply the base tile, right? You can just rotate the base tile like clockwise once, and then you get what you need. This is the base case. Now, the interesting part is the inductive step, right? We assume that px is true. Assume the previous step is true. We want to show whether the next step is true or not. Okay, so we start out with k equals to x. Try to see whether the next step here, k equals to x plus 1 is true. Okay. Okay, give it a bit of thought if you like. I'm gonna stop. I'm gonna resume in like 3 seconds. Okay, so the idea here is you try to make copies of L tileable space that satisfies the previous step, p of x. Okay, put it in this manner. So you see, this is the first tile, the first space that satisfies the previous step. This is the other one, but I rotate it. Here's another one, but again, I rotate it as well. And here is the exact same copy as the upper left corner. Okay, and I think it's pretty clear from the empty space here. The next step is to just insert the base tile. And suddenly we already have the p of x plus 1 satisfied. Okay, so we have proven that using the fact that the previous step is true, then we can just use copies of the previous tile, put it together, and then we get the next step. The next step is true. We can just tile this space using this kind of like formula, so to speak. Okay, so yeah, we have proven the base case, we have proven the inductive step. Then you can just say by mathematical induction, base case is true, then you can, and the inductive step holds, then that means it holds for all positive integers k. Okay, I hope that makes sense. Do digest it if that wasn't. Next, we'll talk about the proof by strong induction, okay, which is the variant of induction. So the idea is very similar to regular induction. We have base cases, sure, base cases is true. And I want you to remember that there can be multiple base cases. Sometimes it's possible to prove things with like limited base cases, but I think it is easier if you have multiple. Sometimes like proving Fibonacci, using base cases, using multiple base cases is easier. Okay, so the inductive step, this is where it differs with regular induction. You assume that all of the previous step is true, P0, P1, all the way to Px. Okay, the difference here is in the regular induction, you just assume the previous step. Just say the previous step is true. In strong induction, you assume everything, P0 all the way to Px is true. And we just show that P of x plus 1 is true. Here by right, I should start with the base case, right? But I'll just assume that P0 is a base case. Let's say your base case for some reason is P of 4, right? Then this should start with P of 4. So here's an example. Let's say I have a country with n cities. Any two cities are connected by a one-way road. Also, what this means is that if I have a one-way road from A to B, I can travel from A to B, but not B to A. Okay, so it's just a single one-way road. We want to show that there is a route that passes through every city. You can start and end anywhere. And here's a little diagram. Let's say I have 5 cities here. So everything is a one-way road here. So there's only arrows pointing a certain direction. I can only go from B to A, but not A to B. And here is the route that passes through every city. I start off from B, I go to D, go to A, go to E, go to C. We want to show that this is true. It's always possible to find such a route, no matter how many cities are there, provided that you only have one-way roads between every city. So here's the statement, the PK. Given the country of K cities connected by one-way road, we claim that this statement says, is there a route that passes through every city? By strong induction on N. And by the way, I noticed I didn't really talk about this term here, but usually we say, so on the things that you are like doing induction on, the n plus 1, usually we describe the vocabulary as like strong induction on that particular variable. Okay, so maybe you can do in graph examples, maybe you do induction on the number of nodes, or maybe another example is if someone else does an induction on the number of edges, right? So that's the terminology. So base case, K equals to 1. We just simply have a country with one city. Simple. That just one city is the route, is the city itself. You start with A and then you're done, right? P1 is true. Base case is trivial. But inductive step is where it's interesting. So let's say assume P1 is true for everything from 1. Remember, the base case I started off with was 1, so I didn't put 0 here. I want to show that P of x plus 1 is true. The next step is true. Okay, so here's the idea. Let's start off with the country with x plus 1 cities. So here I have let's say I have x plus 1 cities. I didn't draw everything, of course. I didn't draw the entire connection to save space and reduce complexity. What happens next is that, oh, okay, I should really give you some time to think about it, but never mind. But anyway, so let's choose an arbitrary city, right? It can be anything. Let's say I chose this particular one and I call it city A. Okay, I call it city A. And then what I do next is I take this city A out, consider all the one-way road involving this city A. I separate into 2 sets. One set is the set of cities that lead to A. So this points to A. The other one points out. Okay, and we are guaranteed really to have this because every city, every pairs of cities have a one-way road. Okay, makes sense so far. Now, okay, maybe I'll give you like 2 or 3 seconds to think. Why is this useful? What can we do next? How can we invoke the inductive hypothesis? Okay. Okay, I'll go on. Then the question we should ask is really, what's the exact size? Do we know the exact size of the 2 sets here? And we don't really, because maybe there are like 4, there are 3 here. In some cases, maybe there's 1, there's 7 or whatever. All right. We don't really know the exact size, but we do know that it has to be less than x plus 1. Okay, we took out CT, we start out with x plus 1 CTs, take out A, right? So no matter how you divide this set, it has to be the case that it's less than x plus 1 because we took A out, okay? And this is where our inductive hypothesis can fit because we have a CT that's less than x plus 1 or equivalently at most x. We can invoke the inductive hypothesis on both sets, okay? So invoke the inductive hypothesis on both sets. And then by the inductive hypothesis, we have a route in that smaller, so imagine that this is a smaller country and this is another smaller country. So the inductive hypothesis says that, hey, let me handle the smaller country for you. I know there has to be a route. You assume me to be true, there has to be a route in the smaller country. So let's say this is the route and this is the route in the smaller country. And here I do say both sets, but a little technical detail is that I didn't really talk about what if like the set is empty, like there's no longer like outgoing edges from node A. So let's ignore that technical detail for now and just focus on like the main case, the bulk of this discussion, right? So we invoke the inductive hypothesis for both sets. And then what we do next is take the last city in this set, in this country, and take this path, take this route, take this edge, right? Take this one-way road going to A, and from A, go here, go to the first city in the other country. And with that, just like that, you have the complete route covering all the nodes. By our inductive hypothesis, we covered all the two separate sets, and then we managed to connect the two countries together like this, okay? And we're done. And okay, again, done condition on the fact whether you have proven the fact that what happens if there's an empty base case, right? So the question maybe you might be asking is, should I use induction or should I use strong induction? And well, turns out that strong induction and the regular induction, they are equivalent, like they can prove the same things by right. But sometimes I think it's easier to prove one using rather than other. For example, actually, the strong example on the countries and cities I gave you can be proven using regular induction, which where I got the example from. You can have a look. I put a reference link. But my personal experience, few examples involving trees and graphs, like earlier just now, it can be modeled as a graph, right? Strong induction really makes it easier because like after taking off one node, you don't really know whether the number of nodes in the smaller graph, smaller tree, how many there are. So you want to assume that everything is true. Okay. Yeah. So further reading proofs. Okay. So yeah. So combinatorics is next. Before that, I think I'll pause this video myself, this recording. But I think for you, I'll resume like in an instant. So I'll take a quick break. I'll pause recording. Okay, I'm back. Although I think in the video, I should like just say BRB, then I'm back immediately, but never mind. Combinatorics, let's go. So combinatorics, let's first talk about permutations. And I think by now you've seen permutations a lot, and just to refresh, it's all the possible arrangements. Like layman is like all possible arrangements. So all permutations of A, B, C is such, okay? And let's say I have a set of n objects. How many permutations does that set have? Okay, so this is the question we want to ask, and how you can kind of like derive this is, let's say each slot represents here a number of ways to choose an object for that slot. So we are like imagining placing it in order, right? Placing it in sequence. So choosing the first element, there are n ways because we still have all n objects. So we take one out, and then choosing the second element is n minus one. We have n minus one choices because we are left with n minus one objects. So well, we only have n minus one objects left. So those are the number of choices, and so on, all the way to one. So number of permutations by the multiplication rule, which I think by now, I hope it's familiar to all of you, is n times n minus one all the way to one, becoming n factorial. Okay. R permutation is slightly more interesting. In case, so you have n objects. Instead of taking everything, let's say some limitation only allows you to take R, where R is less than n. Okay, maybe if you have an object, 5 objects, you want to take only 2 objects. Okay, and also denoted as NPR. Okay, I use Google Slides, so I didn't really do some fancy typesetting here. But let's say put the two permutation of A, B, C, D. So with these four characters, I just simply take two objects and find all permutations. This is really A, B, B, A, A, C, C, A, and so on. Okay. How do we compute that? It's essentially the same thing, but this time we are limited to R slots. Okay, we only have we want to take R things, so we have R slots. Each slot represents, yeah, so the same thing as before. So we want to choose the first element. There are n such choices. Still, we have all the pool of objects in our available for us to choose. Then we choose the second element. But this is where things get interesting. When does it end? It actually ends all the way when R slots are filled up. So this is choosing the rth object. At choosing the rth object, we actually have n minus r plus 1 objects available to us. So you can think of like it as like you have chosen r minus 1 objects. So for the rth slot, you do n minus bracket r minus 1, leading to n minus r plus 1. Okay, so I hope that makes sense. And so basically, NPR is equals to n by the multiplication rule times n minus 1 all the way to n minus r plus 1. This is the first version of it. The second version is you can simplify it in terms of factorial. N factorial divided by n minus r factorial. Okay, so great. So this is permutations of selected elements, NPR. And in case you aren't convinced with the two versions, like first version and second version, I compare it here. I start off with the second version. Let's say I expand it. So this is factorial expansion, this is factorial expansion, right? But the important bit is notice that this n factorial also covers n minus r all the way to 1. So you can actually cancel them off, right? Take the numerator, the part that's common, cancel it off. And then you are left with what you started with, the first version. Okay, great. So permutation of selected elements. So next up is the combinations. So R combination of a set of n elements is a subset R of the n elements. So previously, I take like R objects, I care about their order. In combinations, I don't really care about the order. I just want to know how many ways can I choose, right, without caring about the order. Also denoted as NCR, pronounced N choose R as well. So for two combinations of AB, we have AB, AC, AD, BC, BG, CD. Okay, you can stare at it, convince yourself that this is the two combination. So there is actually a connection between NCR and NPR. Okay, and I prepared this slide because I like, in case, say, for example, you forget how NCR formula is, I kind of like derive it myself this way. Okay, so let's say we consider a set ABCD. Let's consider the NCR and the NPR of it. Okay, the two combination is, as I mentioned before, it's all these, and they're all unordered. I don't really care about their ordering. Okay, AB and BA are the same thing. But when you consider the two permutations, they become ordered. Okay, AB, you flip, you care about the ordering, becomes BA, AC, CA, AD become DA. They are these different things. You care about the order. Okay, so with that in mind, what's actually happening is that for every single one of the two combinations, you set an ordering, you multiply by 2 factorial. Okay, so I put bracket factorial here because I'm scared people think this is the exclamation mark in the English sense, but this is really 2 factorial in the mathematical sense. Okay, and say if you have 3 objects ABC, you want to order it become all 3 factorial permutations of ABC. Okay, so I hope you can see the connection here. Okay, sorry, that was, if you heard it, I think that was my Google calendars, but please ignore that. So therefore, n choose R times R factorial. So n choose R, every single one of them, give an ordering to every single one of them times R factorial is equals to NPR. Okay, hope that makes sense. If not, let it sink in a little bit. From the previous slide, we have this. So we can simplify n choose R. So this is another way to write n choose R equals to the NPR, this is NPR, divided by R factorial, okay, or times 1 over R factorial. And this becomes our n choose R formula. Okay, so in case you forget how it's derived, or you just want to remember the formula, then this is how it is. Okay, Next, I'll talk about the pigeonhole principle. And this is one of my favorite counting principles. It's very logical, but somehow it can be solved. It's useful in solving many different things. So let's say we have a simplest form, right? I won't talk about the generalized pigeonhole principle, but let's just talk about the simple one first. If we have n pigeonholes and I have at least n plus 1 pigeons, one pigeonhole must contain more than one pigeon. So yeah, this is really the image. Let's say I have 3 pigeons, 3 pigeonholes, and 4 pigeons like flying in. Then it has to be the case that at least one thing must like go into something that's been occupied. Okay, we don't know which one. It doesn't say anything about which one, but we know that one of it must contain. Okay, and the application of this is really like trying to identify which one is the pigeon and pigeonholes. When you're faced with a question, identify the pigeon, identify the pigeonhole, then you're done. You're Gucci. Okay, so here's an example. Let's say there are 365 days in a year. How many people do you need in a room to guarantee there's at least one pair of people who have the same birthdays? Okay, so I'm just saying that as long as they have the same birthday, I don't care which day is it. As long as they have the same birthday, it's true. It's good. It satisfies this condition, right? So give it a bit of thought. I'll go through it in like 3 to 5 seconds. Pause the video if you need. And I'll go. Here again, identify the pigeonhole and pigeons. And the pigeonhole here is the birthdays. So the number of days in the years. There are 365 such birthdays. And the pigeon is the number of people. So how many people do we need? Since we have 365 pigeonholes, we need 366 pigeons, which are like the people, right? To guarantee that one of it has 2 pigeons. I guess you can think of it, sometimes I like to think of it in terms of like, oh, I have 365 pigeonholes. What if I have 365 people exactly? Then I can like distribute those people into the same birthday, and I don't have this guarantee of at least one pair of people having the same birthdays. Okay, but if I just add one more person in, then it has to go into a slot that's more than one person that has already has a person. Okay, so pigeonhole principle. There are more nice examples, but I won't go through it. You can look it up yourself. And yep, so this is exercise on combinatorics. Although it's an exercise, but I like you to kind of like know this fact. If you have a set of size n, total number of subsets is 2 power n. It's useful to know this number. Okay, and yeah, so prove this combinatorial identities. And I provide a hint here. I won't read it out in case you don't want spoilers, but I grade it out so that hopefully it's not attention grabbing enough. But yeah, try these out. And finally, let's talk about graph theory. And again, I'll take a quick water break. I won't post the video. I think I can still go on. Graph theory, right? So a really big thing in computer science, graph theory, not the typical like math y-axis, x-axis graph. Okay, let's quickly revise graph definitions. Graph consists of V, a set of nodes or vertices, and E, a set of edges. So I might use nodes and vertices interchangeably, but I hope by now you are familiar enough that you know what I'm referring to. Okay, so for example, we have this graph over here, 1, 2, 3, 4, 5, with these are the set of vertices and these are the set of edges. Okay, the edges are usually denoted as a pair. So depends on whether it's undirected or directed graph, can be unordered pair or ordered pairs. For this example, it's undirected. For example, this edge 1, 5 is here in the set, and the node 2 here is also in the set. Okay, set of vertices. So let's try to recall, like graph is like an abstract concept. How do we represent it in a program? Okay, and this is important in analyzing, say, algorithms, because the runtime of your algorithms depend on your graph representations as well. If you run some maybe Dijkstra using an adjacency matrix, it may run differently if you compare with using an adjacency list. Okay. There's also edge lists, which I won't be covering it in these slides. You can read it up yourself. And so how to represent this using an adjacency list is an undirected graph. So I represent it with an array, let's say array representing the nodes, or it can be a dictionary as well, I guess, dictionary or hash map, hash map, key value pairs, the key is the node. The pair, the value is actually a linked list representing the other nodes it is connected to. So for example here, this is the node 1 here, and it's connected to node 2 and 5. And then this node 2 is connected to 3, 1, 4, and 5. Node 3 here is connected to 2 and 4. Okay, and so on. Here is another representation, the adjacency matrix of an undirected graph. And we talked about matrix earlier in this video. So matrix of A, AUV equals to 1 if and only if the pair UV is element of E. Okay, element of the H set. And I want you to notice later on that this is a symmetric matrix. And you can think about why it is symmetric for the undirected case. Okay, so here's an example. Like let's say I have a node 1 here, right? I look at the row index, row 1, and then it's connected to 2 and 5. So what I do is I fill up the 1, 2, and 3 of the matrix with 1, and the 1, 5 matrix with 1. Okay, this node 2 here is connected to everyone, 1, 3, 4, and 5. So I put everyone with 1. Okay, so this is adjacency matrix in an undirected graph. Oh, okay, I have another example, but yeah. So let's say we change the specification a little bit. We work with directed graph. So it matters whether you go from 1 to 2 or 2 to 1. Okay, so the same thing, representation, but you only care about what it is connected to. Like 1 here is connected to 2 and 5. But the node 2 here, everyone points to node 2. It doesn't have any outgoing edges. It doesn't have any outgoing edges, so the linked list here is empty. For 2, then for the node 3, it only goes to 2, and so on, right? Adjacency matrix of directed graph is the same definition, but it matters. Now, UV is an ordered pair. UV is different from VU if edges are directed. So like for example here, 1 is still to 2, 1 is still pointing to 5, so I set it to 1. But right now, I cannot say 2, 1 is in the set of edges, right? Everything is pointing towards 2. 2 doesn't go outwards. So this row is empty. Okay, 3 is pointing to 2 only, and so I set this value only to 2. Okay, I hope this makes sense. Now, well, we are concerned as well about the space complexity you representing this, so give it a bit of thought. In case you forget, this should be, I hope this is fast enough for you. Space complexity using a adjacency list is OV plus E, while adjacency matrix is OV squared. Okay, when to use which representation, it depends. Okay, now let's talk about the concept of degree of a graph, or degree of a vertex, degree in the graph, right? So the header really should be talking about just degree in general. But let's say V be a vertex in graph G. The degree of a node V, the vertex V, denoted by this, is the number of edges incident on V. You can think of it, how many edges am I connected to? So this vertex has degree 3 because there are 3 edges connecting that is incident on it. And then here's another concept. There's a concept of in degree and out degree in the case of directed graph. Okay, so in degree is incident edges that are incoming. So here in this example, there's only 1 incoming edges. Out degree if it's outgoing. Okay, there are 2 outgoing edges. Now, this brings us to the topic of handshaking lemma. Handshaking lemma is this cute little lemma where it says that, okay, let's say we define total degree of a graph G is the sum of degree of all vertices in G. Okay, the lemma says, okay, this lemma says that in undirected graph G, total degree of G is twice the number of edges. Okay, twice the number of edges. And so I want you to keep this lemma in mind, because personally for me, I've had to use this lemma several times to prove graph properties, or even to analyze the runtime of algorithms. If, like, for example, analyzing BFS, DFS, depending on implementation, it's like strictly neater if you use the handshaking lemma in a sense. Okay, but ignore that if you don't understand it. But just keep this lemma in mind. And here's the proof, or rather the proof idea, okay? The idea is we consider every single edge, right? So we consider from the right-hand side rather. Each one of it contributes to twice of the degree, okay? So for example, if I take this edge over here, it contributes to this degree in node V and node 1, then it contributes a degree to node 2. But what matters is that it only contributes 2 to the total degree. And in the graph, you can't have like an edge pointing to nothing, right? Connected to nothing. An edge has to connect to nodes. So another one between 1 and 5. And you can quickly see repeating this concept. Then you can have like the entire, once you have the entire edge covered, everyone contribute 2. So twice the number of edges equals to covering all the degree, total degree of the graph. Okay, so this is the handshaking lemma. Let's talk about the types of graph next. So in graph theory, we have this concept of complete graph where all the pairs are connected by edges. Like you can see over here, this is the complete graph of 5 nodes, okay, A, B, C, D, E. Then the question is, I want you to consider how many edges are there if there are n nodes. So in a complete graph of n nodes, how many edges are there? Okay, think about it a little bit. And the answer is n choose 2 equals to n times n plus 1 over 2 equals to O(n) squared. And really, we care usually about the order. If we have a complete graph, then we have O(n) squared edges. And usually this is a bottleneck, which is sometimes, most of the time, unfavorable. Okay. Now we'll talk about the bipartite graph. Sorry. Okay. So I won't really talk about why this is the case. In case you don't see it, try to think about it yourself a little bit more. Okay. So now I'll talk about the bipartite graph. So bipartite graph is a graph whose vertices can be divided into 2 disjoint sets. Okay. U and V, every edge connect across the set. Okay. So within the set UV, now the vertices are connected. So this is an example here. So this is the set U, this is the set phi. And one thing to, like, intuitively, you can think of it as the edges only connects across the set, but none of the edges connect within the set. None of it connect within. So it only connects across. Okay. So it only connects across. Then yeah. So these are the 2 examples of bipartite graph. And there's a name for this one. This one where you have like every pair connecting the 2 sets. It's called a complete bipartite graph. Okay. So now finally we have DAG in the example I have in the slides. So in the COVID era, let's not spread germs, right? So stay safe, everyone. So directed acyclic graph, really. DAG, DAG is directed acyclic graph. And so let's talk about the definition a little bit. But I think some of it is pretty clear. Directed means it just has directions. Acyclic means that it has no cycles. Okay, so this graph is an example of a DAG. It has no cycles. And here's an example where it is not a DAG. Why? Because it has a cycle. Okay, it has a cycle. I hope that's pretty clear. This is a type of, like, one type of graph that can be useful. Okay, next thing is topological ordering. So given a DAG, like this DAG over here, the problem of topological ordering is coming up with a sequential ordering that only points forwards. Okay, so like shop, you must first do shopping first before you can do some beat eggs or measure flour or sugar, right? So this is what I mean by only point forwards. If you draw all the edges kind of like only point forward. There's nothing that points backwards. Okay, so another very example, like all of you are students, so like module prerequisites, in a sense, they kind of form a DAG. So let's assume like it's a healthy case, right? Like one module unlocks the other, that module unlocks the other, but some modules may require 2 prerequisites. So that's a DAG, right? In most cases should be. I haven't thought of like possible cases where the module prerequisites have like dependencies, right? That's bad. You need to take module A if you take module B, but to do module B, you need module A. That's bad. Okay, never mind. So these are the types of graph, and let's see. And yeah, so these are the quick intro to graph, and I won't go through the graph algorithms, but these are the things that by right you should already know. things like depth first search, breadth first search, topological sorting, Dijkstra's algorithm for SSSP, Bellman-Ford for SSSP. So this should be familiar with you by now. If you don't remember the details, that's fine for now, but please do read it up. Do read it up before like the STEM gets heavier. Okay, some of you may be familiar with Floyd-Warshall algorithm for all pair shortest path, but I don't think all the classes, at least in NUS, covers Floyd-Warshall. Those took 2040 years under Prof. Seth Gilbert should cover this, for example. Okay, so next I'll talk about trees, which is a special case of graph where it's a connected graph with no cycles. Okay, so these are some equivalent statement on trees. So when I say that T is a graph with no cycles, it also means equivalently is the same definition to say that every two distinct vertices in T are joined by a unique path. Okay, try to verify in this diagram over here. Let's just take A and F. I can only go through A, B, C, D, G, F. Okay, there's no other path that connects A and F. Similarly, let's say D and E. Okay, I can only go through this DCE path and just verify for every distinct vertices, they are joined by a unique path. And why I mentioned this in particular is because I've had to do an algorithm, to like design an algorithm where I make use of this particular property. I'm given a tree, and then I make use of this particular property that every two distinct vertices in T are joined by a unique path. So the idea of like, just to give you an idea of that question requires me finding two nodes in a tree. And then what I did is that starting from connecting those two nodes, I guarantee that a single path, unique path, and then I do a binary search on the path, okay, on the vertices along the path. So that was kind of like the idea of like one of the questions I had to do before involving this property of a tree. And yeah, the finally here is just like a simple statement on the size. So if I have V vertices, then the V is equals to number of edges minus 1. Okay. Okay, wait. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Oh, okay, I think I mixed this up. It should be E equals to V minus 1. Sorry. So yeah, there's a typo here. Sorry. I'll fix this in the slides afterwards. Yeah. So yeah, my bad for the typo. And okay, so we are coming to the end of the slides. Spanning tree is an acyclic subset of the edges that connects all nodes. So okay, now, sorry, I mixed up the concept a little bit, but now we are starting off with a graph. Like, let's say we have a general graph. And then the spanning tree of that graph is the subset of edges connecting all the nodes in that graph. Okay, so like here, the actual graph connects between these two nodes, but the spanning tree only cares about like these set of edges. Then once you have it, it's kind of like find the tree that is a subset of the graph, but collecting all the nodes. Okay. Then the question of minimum spanning tree is really finding the spanning tree with the smallest weight. Okay, 4, 1, 2, 5, 8. So like just now, you have this spanning tree, but you can also have this spanning tree. Okay. I guess an interesting question to ask is like, how many spanning trees are there possible? I learned this in MA2214, Combinatorics and Graph, and they do have like complicated formula or like complicated things to do it. That counting involves some matrix determinants and things like that, if I'm not wrong. Okay, but never mind, not required for this course. I believe. Okay, but don't quote me on that. Okay, so algorithms for minimum spanning trees, you may or may not know Prim's algorithms or Kruskal's algorithms. This depends on which class you took, but do learn them if you haven't. Okay, so a Prim's algorithm requires you to know a little bit about the binary heap priority queue data structure. Kruskal's algorithm will require you to know a little bit of union find data structure, the disjoint set. UF, yes, union find disjoint set. Yeah. So another MS-state algorithms, I believe if you look CS3230 under Prof. Seth Gilbert, you have talked about Borovka's algorithm. But personally, I think this is rarely discussed. You can also have a look if you want to. But yeah, more importantly, do look up prims and cross goals if you haven't already. Okay, so with that, that was a lot of content. We are at the end of the content. If all of those were easy for you, that's great. Okay, and if you are uncomfortable with it, do spend some time revising, because I understand some of you might forget the discrete mathematics stuff, or maybe you didn't start off really well in discrete math, but it's not too late. It's not too late to pick it up. Okay, try your best. Do spend some time revising. And yeah, just again to emphasize, I couldn't have covered everything. Discrete math, like CS1231S is an entire module over span of one semester, but I couldn't have possibly covered it in just one slide, one set of slides, right? So I tried to cover tools and techniques, which I think you might often need in 3230. I hope that is helpful in the weeks ahead. And yeah, so yeah, all the best for CS3230. I hope this slide was beneficial for you. Do let me know if you have any feedback, you spot any further typo, or like I said something in the slides. I'll upload this video somewhere and probably like make erratas along the way. Okay, so all the best for CS3230. Don't burn out in the semester. Things can get pretty heavy. Seek help early. Okay, so find the TAs, find the lecturer early, and start assignments early, and so on, right? So yep, I think that concludes it. I will now stop sharing, and yeah, I guess I'll stop the recording now. Okay, have a nice day.